This is their weekly refresher session, Tuesday mornings. And today we're talking about power flow and load flow. And at this point is really the benefit and the ability to get a return on the investment if you've utilized EasyPower for ArcFlash, because the same database that's created for ArcFlash can then be utilized for other additional studies and examination of the system, and probably there's no better return on that investment than using the power flow or load flow module. So load flow is a numerical analysis of the flow of electric power in an interconnected system. It's a combination of calculating the DC resistance and the reactive impedance and the resulting current when a voltage is applied, an alternating current of voltage is applied to that impedance, and then the reiteration until you get a resolved numerical solution that solves all the equations simultaneously. Focuses on voltage angles, real and reactive power, and it can be extremely valuable in planning for future expansion as well as optimizing the operation of the system today. And what we're going to be doing is going through a few examples of that. And if at this point in time you're not hearing the audio, please send me a chat and let me know that my screen is offset. Okay, that's a good one. All right, so the question arises, when did power flow become so important? And it turns out, long before there was discussions about ArcFlash, long before there was discussions or need for thermography, even before the fad to talk about power quality, there was load flow. And it turns out it was actually a key metric as they were having the tussle over whether an AC or DC distribution system was the way to go, when Thomas Edison and Tesla and George Westinghouse were all doing their thing at the turn of the century in the 1890s. So the bottom line, it's a way to take your one-line diagram and extract from it specific results. So this is a screenshot of the tool, and what it gives us is the ability, as we control, let's see if anybody else is chatting me, as we control these icons here on the top left, we have the ability to turn on and off different parts of the display based upon what we're trying to focus on. So initially the buses can be set up to show per unit voltage and then the power angle, and the power angle will change as we have more or less reactive loads in the system. We can also display the generator load data, generator and load data. In this case we're showing the megawatt flow and the megavar flow. So this is real power and this is reactive power supplied by the utility in this case. And this is the real power and reactive power that's being used by the load. Likewise, we may want to look at the flow through different parts of the circuit, comparing the real power and the reactive power flow. And where we see a difference will be the sources of losses. And in this case, we're seeing a significant drop in the reactive, well, significant, we're seeing a drop in the reactive power and somewhat in the real power across the transformer, and that will show up as heat dissipation in the transformer itself. Now obviously there's going to be a certain amount of loss in cables and in any of the elements, and optimizing that is part of the task or part of the function of utilizing the load flow analysis. Likewise, we can see voltage drops across these same elements. In this case, we're seeing almost a 1% drop in voltage across the transformer, and just a minor negligible drop through this cable in this simple one-line diagram. And likewise, we can see transformer taps, overloads, voltage violations, and as important as anything will be the ability to pick out or pinpoint losses that may be in reactive power or in real power. So in this case, what we're showing is a 6.5 kilowatt loss across the transformer, but 104 kilovar loss at the same time. And these are areas where we may want to mitigate or take some steps if we are experiencing a loss in reliability, or maybe even a loss in ability to deliver power to a load. In addition, the load flow tools can perform impact motor start, and this is a very nice way to determine whether or not the system is being overloaded as we're starting the motor. And there are a lot of variables in this case. We're looking at a huge motor, a 5,000 horsepower motor, and we would expect to see a fair amount of voltage dip when we start this, and the potential to actually overload current that are supplying it, because starting currents will be much higher based upon the locked rotor multipliers that are being used in the motor. So we're going to show some of these examples. So what we can do with the tools is look for overloads. We can isolate transformer losses and be able to potentially coordinate them to higher temperatures that we can measure. Also, the ability to correlate preventive maintenance if the measurements we take aren't matching the model's results. And what the tool gives us is a baseline, and as we compare that against our actual measurements, we can determine two things: one, if the model is correct or not, and how much the ideal or design system varies from the real system as things are being measured, and it's that difference that allows us the ability to improve the operation of the system. Another area where there can actually be a realizable cost benefit is the ability to mitigate power factor demand penalties if we've been able to identify them and if they're showing up on our electric bill. Question came up last week regarding flicker and the causes of flicker, and we were talking about short circuit, but it turns out it's not so much the potential fault current that causes flicker. More likely than not, it can be caused by a very quick dip in power interaction when we're starting or overlapping large load starts, like welding machines or arc furnaces, or even large motors. And it's this quick dip in the power or the voltage sag that will cause flicker. And if you have a resonance, it can actually impact or be manifested in lights flickering. So there's ways to deal with that, and load flow is one of the first things to look at. Likewise, you can also look at what-if scenarios. If you have the need to understand what your system's going to do if you make changes to it, load flow is actually the first place to go. And so, and I think that's probably the most obvious day-to-day use of the tools for that point of view. And then you can also use load flow or power flow to determine whether your data collection during an arc flash study is accurate or on track. Okay, so here we're going to run through some examples. They're not necessarily, these are illustration purposes only. They're not necessarily recommendations for sound engineering design. Let me open up the tools here. First thing we're going to look at is a standard arc flash example, and if you've seen me do an arc flash demo, you probably see that we'd end up somewhere along here, and at this point we've done an arc flash study. Things seem to be fairly benign, and we calculated or produced tools. All right. If we pick up the power flow module and do a quick study, we enter power flow, we solve, and we're able to display the voltages. All right, so this is saying that the utility is coming in at 1 per unit with a 0 phase angle. By the time it gets across the transformer, we've got a 0.996 per unit voltage and a slight shift in the power angle. One of the first things we want to do when we start to use power flow is make sure that we have made adjustments to our database. As you recall, when we do an arc flash study, we're basically filling in the first 3 or 4 tabs on the data dialog box. When we're going to do power flow, we want to make sure we enter data or modify the data that's required in the power flow tab. Probably most important is the scaling factor, because as we go in and look at each of the systems, as we go into power flow and look at voltage and current, all right, what we see are the quiescent current. This is the kilowatts and kilovars that are flowing in this particular branch. And this is the kilowatts, and I believe if we look at the power flow, we can control the units displayed on the one line from the power flow options. And what we're showing for loads is let's do kilowatts and kilovars first. All right, so obviously if this motor was not running at 100%, and very seldom do all motors run at 100%, this doesn't fairly reflect the condition of the plant. So if we go back into our database editor and change this to the power flow entry to say normally it runs at 60%, then this is going to better reflect what the actual current is for this particular motor. So this right now is representing the kilowatts and kilovars that this motor load is drawing, and then these will be the power flow of the current through the branch. Okay, so that's what we're looking at here is the voltage on the bus. As I kind of click on the icon, you can see the voltage appear and disappear. We're looking at the motor and load data. Here's the branch flows, the transformer taps, which if we come back up here, turn those on, we just have a straight 12.8 to 4. Then we have the ability to invoke overloads, and where we see anything that's exceeding the branch currents or the voltage violations, they'll highlight in red. All right, for now we're not seeing anything isolated there, so let's go back and try a what-if scenario. What if our plant were running fine and we have somebody come in and say, okay, it looks like you got plenty of capacity on this particular switch gear. What would happen if we replaced this 10 horsepower motor out here with a 250 horsepower motor? Will the system be able to take it? So again, we'd enter 250 horsepower, calculate the full load current, calculate the X over R ratio. Let's go ahead and run this at 100% just to see how it handles the load. Go into power flow, solve, and the first thing you see is that we're real close to overloading this particular cable. And the same thing is true up here with this cable where it's rated for 310 amps and we're at 386. So the first question is, okay, more than likely we got to resize the breaker, and the cable that runs out to the motor and this main cable coming down from the main switch gear are going to be our biggest problem. Likewise, we can see what happens to the voltages. The voltage drop here doesn't look like it's out of the ordinary. We're just below 0.98. If we want to look at real actual units, we would change the per unit bus voltage to volts and apply. Now you can see we're down at 469. So that in itself may be an obvious problem for being able to put this kind of a load on this piece of switchgear. All right, so the point is we can see what would be the impact of making a very large change or a considerable difference, and be able to go back and iteratively say, okay, well, how does that improve if we increase this cable size? So let's go ahead and save the changes rather than modify the cable size. I'm just going to use auto design to take it up, go back into PowerFlow and solve it. And it looks like it fixed that one there, but it didn't fix the one at the top. So my voltage is actually dropped. I was at 479. All right, so the point that we're trying to make here is we have the ability to look at voltage drops, losses, and overload conditions, both voltage and current. Let's go look at a more realistic system from a database that was sent in on ArcFlash. All right, so we want to go out and look at this particular crane. So in this case, we have a 480 volt bus that has a couple large motors here, and as just without any other consideration, we put it on a PowerFlow and we look for losses or overload. We see that this cable is running at 91%. Just because this is near the rim or near the rating of the cable doesn't mean it's necessarily poor data, because again, these motors are probably set up at 100%. We go back and double check. You can see right now we're looking at a PowerFlow scaling of 100%. All right, so the chances are that both of these motors are on 100% at the same time is probably not all that harmful. However, once we go in and look at PowerFlow, what are the chances that the motor or the system is impacted by starting this motor? So by double-clicking on the motor and checking this box that says Start Motor, we're going to do the initial solving of equations at 0%, and then we're going to start the motor after everything's quieted down. All right, so we don't have an overload condition as we solve the motor. Now we'll start, or we solve the system. Now we'll start the motor, and you can see that the voltage is pulled down to 0.905. We actually had a surge that looks like it's 300% of what the rating of the motor is, and that's with this motor running normally. If both of these motors start at the same time, the question is what would happen to the system? So we solve it, start the motors at the same time. Now you can see we have a considerable drop in the voltage. In fact, it's impacting virtually every bus in the system. And the question is, how long does that take place? Well, this is the motor acceleration curve, and if both these motors are going at the same time, this may last for anywhere from 1 second to 5 or 10 seconds, and more than likely this will cause a sag in the voltage in the whole system, and potentially even flicker if we have a lot of starts and stops while we're operating the crane. An example of what we can look at while let's kind of take these back and take these off. Put them back at 50%. Okay, so another what-if example might be, as we're looking at different parts of the system, what if we want to operate this bank of motors on the generator for any length of time? How's that going to handle it? And again, just as the motors have the need for some data input on PowerFlow, the potential for having to make an adjustment to the generator data is equally important. And so as we go in and look at this, I just want to point this out as far as data entry. Normally, when we enter the data for a generator, in power flow, we would have it at constant PV, and if that were the case for power flow, we'd solve it, and we'd see no current being generated from this generator, whereas it would be a normal operation if it were on the main bus. All right, so the point I'm trying to make is, in setting up the generator data dialog, for power flow, it would have to be a swing system so it can react to changes in the load and supply both reactive and resistive or fixed loads. So now as we solve it, we can see that if all these motors are running at 100%, that we have a potential for overstressing this cable by almost 50 or 100%. And certainly, as we start any one or all of these motors, I'm assuming that as the engineer designed this, he expected or didn't expect all these motors to come on at the same time at 100%. So in terms of error checking the system during an arc flash study, this is not all that much of a concern because we're still in the ballpark as far as the rating on the cable. For instance, this particular cable, with just the data that we've entered from an arc flash, we're showing that it's within 6%, it's 6% over its maximum rating of the cable, which doesn't indicate that there's a problem at all as far as data collection. It does indicate that the engineer that designed this didn't expect these motors to be running at 100% all the time. Okay, another situation that comes up on a what-if basis, and let's kind of go back to our database editor. Okay, we have a transformer that's gone out or it has to be replaced, and for whatever reason we have the ability to change an available transformer, same size, but it's a delta Y connection. How is that going to affect our system if we go replace out or swap out a delta-delta connection versus a delta-Y? This function is actually not necessarily part of load flow. It is included in standard EasyPower. So what I'm going to do here is describe a new transformer with the same parameters as we're replacing. And we calculate the overload current. Impedance is 6.04. We calculate that. And this, instead of being a delta-delta as we're starting out, we're going to have a delta-Y and neither side grounded, so we leave that okay. Let's go ahead and activate this one and deactivate the other one. And then go to short circuit focus, and the tool tells us that we have a phase shift error because of something that's going on in the in or around bus T8, 9, 10 primary. So if we go look for that, bus T8, 10 primary, more than likely this is going to be somewhere in the vicinity of the transformer that we just replaced, and that's why the tool's giving us an error. For those of you that have run into this, when you're doing an arc flash study and you get this error, it's actually part of the options in database editor to be able to go in and in the system settings, I'm sorry, in the general settings, what we're looking for is verify phase shift integrity of the system. So clearly, if you have a system that's running and you get this error, it doesn't necessarily mean it's a problem with the system. You just need to verify that you've collected the data correctly. On the other hand, if you have a system that's running correctly and you want to go in and change something, it is a good check to make, especially if you're looking at power flow considerations. All right, so where we're kind of leaving this is the ability to do a lot of what-if scenarios in the real-world situation. Everything we've just considered, including adding a large motor, could actually impact the arc flash calculations, in which case we would have to go back and make adjustments to what we've done in arc flash. But the primary thing that we're looking at with load flow is verifying that the system can withstand the modifications that we're trying to apply, and verify that what other elements are going to be impacted or need to be changed. Now, the thing that I haven't touched on, and it's probably worthwhile even here, is looking at the display on each of the loads, in which case if we have a motor-intensive environment, we can look at in the loads and the generators the power factor at that particular point. And so what we're showing here is a 359 kilowatt load, the power factor of 0.82 at 100%. Let me take off some of these displays. And when we go back up to the main utility connection, this is probably can't even find the main utility connection. Let me go to more simplified examples. All right, we go to kilowatts and power factor and apply it. Because we have virtually all motors as loads, what we see here is that we're drawing 358 kilowatts from the utility at a power factor of 0.828. In and of itself, this actually could incur significant power factor demand penalties at most utilities in the United States. Two ways to kind of mitigate that is either reduce your power load or add power factor correction. Power factor correction is a matter of adding some capacitance to the system, and in part its other benefit of adding capacitors is to raise the voltage on a particular bus. So in the case of, let's look at our bus units. All right, so here we've had the bus voltage pulled down because of the load on the system. And if we take the load off, we can see, and this is a very large motor, we can see that the voltage on the bus goes up considerably. So one way to kind of deal with that, and again, this is not the way the designer necessarily goes about things, but is to see what the advantage of adding a capacitive element into the system. And as we do this, we just kind of put in a switch so we can see the effect. All right, so we go into power flow, solve the system. And as we take the capacitor out, you can see that the power factor, and I lost my loads. So it brings the voltage up on the bus, and in this case it brought it up quite a bit, but maybe not enough to make us happy. But it did bring the power factor back up to 1, So, and obviously I'm just winging it here, but that's the net effect. In this case, we had a very large motor, but at the same time, to offset it, we have a large capacitor. And obviously, if what we're trying to do is bring down our power factor correction, then it's not necessary to add in that big of a capacitor. But that's one way to bring your bus voltages up on remote buses, or to deal with the power factor correction incurred by, or power factor penalty incurred by large motors. Okay, so you have a lot of jitter between, you know, I'm thinking, so there was a complaint, I guess, about the website itself, this display, and so I think we may have a little bit of interaction between the screen resolution and the display, so I apologize for that. Okay. Scaling factor and duty factor are the same. No, so that's a good question. All right, so in the world of power systems design, duty refers to how close to the maximum rating a particular device is being used. And particularly in protective devices or bus systems, the duty refers to the maximum interrupt current that it's guaranteed to perform at. So if we look at, I'm in short circuit focus now, we're going to fault the buses, I'm going to look at branch current. One of the requirements for arc flash is to examine equipment duty. So this little icon at the top left says equipment duty. If I display that, it goes in this case gives me a display of anything that's not meeting the equipment duty guidelines, and it also produces an equipment duty report. So what this is showing is that BL5 and 6 were tested at the factory. BL5 is guaranteed to withstand 30,000 amps, and so it's only seeing a 21,000 amp hit when it's at faults. So its duty is 70%, which means we have about a 30% headroom and safety margin. Likewise on BL6. So this is what's referred to as duty in a power system design. What we're talking about as far as the scaling factor is the amount of what percentage of the performance of that particular motor is normal or average, and that's how we're kind of sizing the upstream branches, and it has nothing to do with the protective devices. So it's very much a different use of the term duty when you're talking about power system design. So good question, and if you got more questions on that, please send me an email, because it is important to understand that, especially when you're in the arc flash mode. Okay, looks like had a bunch of problems with the display, so I apologize for that. Any other questions? Scaling and diversity, that's a good question. So the answer is no, it's not the same. And again, it depends on how you're describing diversity. When we go to design our system in database editor, we have the ability to describe certain loads with a thing that's called diversity. And essentially, what we're talking about is whether or not how the utility company considers that particular load in terms of the rating or the diversity and importance of that load and this, I think, is portending towards more capability in the smart grid. And that is, let's see if we can kind of find an example where we have a switch gear, we have a device rating, condition rating, and diversity. What this relates to is Well, I guess I take that back. You could use these as the same, in relatively the same way, but in reality, what we're talking about, I guess, is code factor. There's three terms that kind of come into play. Code factor is more the one that the utility looks at. Diversity, yes, I think it can be interchanged with scaling. What and why it shows up on a display for switchgear is these can be dealt with on a global basis, whereas an individual motor, the scaling factor, is handling it as we're analyzing power flow for that particular motor. So I take that back. Scaling factor and diversity are similar. Okay, I think that kind of covers what we were intending to talk about. Again, if we see excess losses across a transformer, we'd want to verify basically the temperature reading and schedule PM. We looked at replacing motors, adding extra loads, what system elements could be limited as far as their rating. One of the first things I do when someone sends me an ArcFlash database is run power flow just to see if there's any gross errors. When they're off by a few percent as far as the cable ratings, it's probably not an issue, but if we're off by an order of magnitude or 3x or 4x, then we probably have missed something on the data collection mode. And I think that's all I want to cover for today. Appreciate your attending. Feel free to send in emails either to techsupport@easypower.com or jim@easypower.com, and we'll talk to you in a couple weeks. I think our next refresher is 2 weeks from today. Have a good one.